Hello everyone, thank you for coming to our talk entitled Medial Spectral Coordinates for 3D Shape Analysis. In this work, we aim to equip present models with an enriched representation of 3D object shape, one that leverages the local width of the object to construct a spectral feature at each of its boundary points. To achieve this goal, we take the advantage of the medial representations. Introduced by Harry Blum, medial axes, or skeletons, have been used in the vision and computational geometry literature for years. Formally, the medial axis is defined as the locus of centers of maximally inscribed spheres within an object. Here, we develop a robust and reliable implementation of an algorithm for computing 3D medial surfaces based on an average outward flux measure. The implemented algorithm follows these steps. We first imagine we have a 3D shape and its boundary given as 3D points. We then compute the Euclidean distance function with respect to the object boundary. Having the distance map, next we compute the gradient vector field and the average outward flux map over that vector field. Using the average flux map, we can apply a topology preserving thinning process to get the medial axis transform. Here, we show a schematic of a portion of a medial surface together with a selected maximal inscribed sphere and the associated bitangent points where the sphere touches the boundary. At the end of the medial surface extraction process, the medial surface can be represented by a set of skeletal points where each point is associated with the following information: the loci of that point in 3D, the radius of the maximal inscribed sphere at that point, and the corresponding average out of flux value. We now propose to use medial manifold to equip the object surface with a new spectral signature, one that explicitly considers local object width. Here I will explain how we do this. Let's imagine a 3D shape such as the one we see here, and two maximal inscribed spheres within this shape. Let us call them rho I and rho j. For each of the boundary points that correspond to these maximal inscribed spheres, we compute a spectral coordinate which is obtained from a spectral analysis based upon the intersection between these spheres. Computing the intersection between rho I and rho j, we can imagine an adjacency matrix that connects every pair of points by a measure that computes how much their respective maximal inscribed spheres intersect. We call this matrix A, and then, using Arnold-Lee method of RPOC, we compute a set of real non-negative eigenvalues and eigenvectors. Information associated with the boundary can later be mapped on the ith eigenvector as shown here. Finally, we take the following measure as a spectral coordinate additional to the location of 3D points. We evaluate the use of our medial spectral coordinates for three popular applications in 3D shape analysis: 3D object pair segmentation of 3D objects, 3D object classification, and finding correspondence between surface points. For pair segmentation, we collect all the spectral coordinates computed and add them as additional features to the boundary representation. We then use the high-dimensional data spectral clustering to cluster all object models within a category together. Our results show that in several of these object categories, there is a boost in performance when we use the spectral coordinates that use medial surface information over the use of raw data. For object classification, we create a new feature vector for each point in a 3D point cloud as a geometry similarity connection, capturing the local behavior of each point in the eigenvector space. We add these additional features to the points features, creating a vector of 9 features for each point in the point cloud. We tested the additional features on the popular PointNet model. The added features result in an improvement in overall accuracy of the model from 88.76% to 90.41% on ModelNet 10 and from 86.23% to 88.26% on ModelNet 40. To find point correspondences, we use an existing technique to reorder and align spectral coordinates. After reordering and aligning the spectra, 2 points that are closest in the embedded representations can be treated as corresponding points across the two objects. The results show the advantage of using medially driven spectral coordinates when compared to the best conformal model that we could find. To conclude, our method combines local surface geometry and regional information in a boundary representation. The skeletonization algorithm has linear complexity in terms of the number of interior voxels, which is a present limitation of this approach. And finally, our experiments show that the use of medial spectral coordinates is beneficial in various 3D object analysis. Here, I want to thank all my co-authors and funding agencies who have supported this work. Thank you.